Hello, and welcome to Greg Does Physics. My name is Greg, and today we're going to be doing a little physics. So for today, I'm going to be doing problem 1.36 out of Griffiths E&M, and it asks us to show a couple of lengthy equations, and it doesn't give you any hints, it doesn't tell you how to do them. But if you've read the section prior, integration by parts, then you might have an inkling for how to do that. But before I go any further into showing how to create those two equations, I think it's good to start at the beginning and kind of show what those equations are analogous to. Now, if you've taken an intro calculus class, be it in high school or college, you should have run into this concept of integration by parts because it's a very powerful tool when integrating some function that you can express as the multiplication of two functions. Say, for example, f of x equals x times e to the x. You can express that as the multiplication of the function x and the function e to the x. Invoke integration by parts, and then all of a sudden it becomes a lot easier to integrate that function. But how do we get integration by parts? How do we derive that? And we basically combine two ideas in calculus to get the equation for integration by parts. And that is the product rule, which is saying that if you differentiate, again, some function that can be expressed as two different functions multiplied together, then it's equal to this. One function times the differentiation of the other plus the other function times the differentiation of the other one. Poor job of explaining that verbally. And the other thing is the fundamental theorem of calculus, which is this whole equation. And what is this equation saying? It's saying that if we have a function f, for example, what we could do is we could take the infinitesimal rate of change of this function with respect to x, that's the df dx, and what we can do is we can multiply that by some infinitesimal dx, and that gives us the infinitesimal change in f, df. And if we add up all those infinitesimal df's from some point A to some point B, that is, if we integrate them, then that'll give us the change, the total change in f from A to B. Or we could just write that as f of B minus f of A to get the exact same change in f over that same interval. Griffiths gives an apt sort of analogy for this. It's the idea that if we wanted to, for example, measure the height of the Eiffel Tower, one way we could do that is we could go up stair by stair from the bottom of the Eiffel Tower to the top with a ruler and measure the height of every single stair and then add up all those heights, and that would give us the height of the Eiffel Tower. Or what we could do is we could just stand at the bottom of the Eiffel Tower and stand at the top with an altimeter and measure that altimeter and then find the difference in the measures of that altimeter, and that would also give us the height of the Eiffel Tower. The left side is adding it up using a ruler, going stair by stair, and the right side is just using the altimeter at the top and at the bottom. So if we combine these two ideas and say we have an integral from A to B of some product of two functions, then what we can do is we can, if we invoke fundamental theorem of calculus, we can say that this is the same thing as that function evaluated from A to B. Or what we can do is we can invoke product rule here, and we can say that this is also equal to integration of this f times dg dx dx plus the integration g df dx dx. And then we can rearrange this to look like integration from a to b f dg dx dx equals a b g df dx dx f d a to b. So what have we done here? What we're saying with integration by parts is that we have the product of two functions. One can be expressed just as a function itself, and one can be expressed as the differentiation of some function g. And what we can do is we can flip the differentiation around, and at the expense of picking up a boundary term, we can make this integral a lot easier depending on what term we have here. And if you, like I said, if you've taken an introductory calculus class, you should know how to apply integration by parts. This is a tool that you should be familiar with already. I'm sorry, I got this wrong. That should be plus and that should be negative. My bad. But yeah, so this is a tool that you should already be familiar with, have in your toolkit, know what this means, know when to use it. But importantly, we're not just going to be doing this one-dimensional calculus. In electrodynamics, we need to be familiar with vector calculus. And so we should be able to guess that if we extend these ideas into vector calculus, we should be able to come up with a vector calculus equivalent of integration by parts, this equation. So Griffiths has already given us earlier in the book different product rules for vector calculus, and we've also picked up the equivalent of the fundamental theorem of calculus. Now, I think one thing that's really useful to sort of pick up is that Green's theorem and Stokes' theorem, or you also might know them as divergence theorem or the fundamental theorem of curls, they are sort of our equivalents of this fundamental theorem of calculus, except when it comes to vector calculus. And we already have the equivalent of the product rules, and so what we're going to be doing for this problem is using the vector calculus product rules and using Green's theorem or Stokes' theorem to create equivalent integration by parts. So let me erase all this. And let's sort of start over, except with vector calculus. Now, let's recall that there are multiple ways that you can create a vector as the multiplication of two functions. So, for example, we could have a vector expressed as a scalar times some vector. So this is a new vector function expressed as the product of a scalar function and a vector function. Or what we could also do is we could have a vector expressed as the cross product of two vectors. And this is another way to create a vector as the product of two other functions. So we have a vector function, and it's the cross product of some vector function A and some vector function B, and we get a new vector function. So there are corresponding product rules for this, and then there are multiple ways we can differentiate when it comes to vector calculus. One is taking the divergence, and one is taking the curl. So these are both two ways in vector calculus to quote-unquote differentiate a vector function. So if you look at problem 136, you see one function f and one function, a vector function a. So that tells us that we're probably going to be using a product rule with this for that. The other thing is that you're going to be seeing a curl, which means that we're probably, for part A, going to be wanting to use the curl of some FA. And so from our product rules, let me get back here, from section 1.2.6, that gives us a bunch of different equations for product rules. And it gives us that the curl of some f, some scalar function f, and some vector function a can be re-expressed as this: f times the curl of a minus the cross product of a and the gradient of f. Okay? Now, what we also should use here is, where did it go? Stokes theorem. It looks like Stokes theorem. We see a closed loop integral for some perimeter, and then we have some integral over a surface. So let's write out Stokes theorem. That is the integration over a surface of the curl of some vector function dotted with dA is equal to the closed loop integral over the perimeter of that surface of that function v as some function, and dotted with dl. So now basically what we're going to do is we have our product rule, we have the equivalent of the fundamental theorem of calculus, except this one is Stokes theorem, and we're going to combine these two. And so if we say the integration of that surface of the curl of FA dot dA, well, on one hand, we can just say that's equal to FA dot DL but we can also invoke our product rules here. So that is F curl of A dot dA minus, over the same surface, A cross product with the gradient of F. That's all dotted by dA. So then all we have to do is reorganize this, and on one side we'll leave this integral over surface f del cross A dot dA, and then we'll add this to the other side. And if we look back at the equation, what the problem is asking us to solve for, we can see that this is indeed correct. And how is this analogous to integration by parts? Well, it's basically saying again that if we have some vector function that can be expressed as the product of the multiplication of some scalar function and some other vector function, and if we want to integrate this over some surface, then what we can do is we can switch where the derivatives, where the differentiation is. No longer are we taking the curl of A, but instead we've now switched it to taking the gradient of F. And then we also pick up our boundary term. And so you can see that it directly correlates to our integration by parts in one-dimensional calculus. It looks the exact same. Alright, now with part A solved, we can move on to part B. Now, looking at this equation, you'll notice a couple things, or you should notice a couple things. In part A, the equation that we're trying to find has two functions in it, a vector function A and a scalar function F. But if we look at the equation for part B, we have two vector functions instead, A and B. And so that tells us that our product rule that we're going to use in this case is probably going to involve a vector that is created by the cross product of two vectors, whereas in part A we're looking at a vector function that was created by the multiplication of a vector function and a scalar function. Now, the other thing that we'll pay attention to is what the integrals themselves are. There are two volume integrals, and then there is a closed loop integral over a surface. And that sounds to me like Green's theorem, or divergence theorem, which involves a volume integral and a closed loop integral over some surface. So I think what we're going to need here is Green's theorem, first of all, so we can write that down. Green's theorem will, in this case, be the equivalent of our fundamental theorem of calculus. And before I go any further, I just want to give a brief aside to maybe explain how Green's theorem or Stokes' theorem is the equivalent of the fundamental theorem of calculus, except in extended, that concept extended into vector calculus. I think explaining how the product rule is extended to vector calculus kind of speaks for themselves, and I've given a little bit of background on that already. But back to the fundamental theorem of calculus. As I mentioned earlier in this video, the fundamental theorem of calculus, one way you can think about it is that it's saying that in the example of measuring the height of the Eiffel Tower, measuring the difference between the top and the bottom to find the height is the same as taking the difference in height over some minuscule step from the bottom to the top. And Green's theorem is kind of similar. One way to express it, well, it involves divergence, and we got to think about what is divergence measuring. And the namesake divergence does a pretty good job of sort of indicating what you might expect it to measure. And you can imagine it to measure for a given vector function how much from a certain point is that vector function diverging away from that point. And so the example that Griffiths gives is that you can imagine some bound volume contains an incompressible liquid, and within that bound volume are faucets that are pouring out more and more of this incompressible liquid. But since the liquid is incompressible, whatever fluid is poured out inside of this volume has to be pushed out somewhere, has to be pushed out of that volume. And so Green's theorem, which takes the form volume integral the divergence of some vector function v d tau equals closed loop integral over the surface that bounds that volume is basically saying on one side, we're saying if this is the divergence, that is how much incompressible fluid is being poured out from those faucets within that volume, measuring that would be the same as looking at how much volume is pouring out at the surface of that volume, because as we stated, it's a compressible. What's created inside there, what's poured out inside there has to be pushed out. That's this idea of flux. The flux through the surface is what we're looking at. And it makes sense how these two quantities will be equal. So that's kind of what it's saying. That's kind of how it's analogous to the fundamental theorem of calculus. Stokes' theorem says a pretty similar thing, except instead of looking at the divergence, it's looking at the curl. And again, the curl, the namesake sort of shows you what the curl is roughly like looking at, and it's how much for a given vector function you expect the vectors to be swirling around a given point. And so you can imagine some area has a bunch of sort of like, what's the word, like infinitesimal swirls, and taking the swirl, adding up the swirling at the perimeter would be the same as adding up all the infinitesimal swirls within that. And that's kind of a very rough description of what Stokes' theorem is doing. And so, anyway, I just thought it would be pertinent to sort of expand a little further on how these concepts are just natural extensions of extending the theories of one-dimensional, single variable calculus into vector, vector mathematics, vector calculus. Anyway, that was a long, sort of long-winded, tangent. But let's get back to the problem. So the other thing, we have our fundamental theorem of calculus equivalent. Now we got to find our product rule equivalent. And if I go back to product rules, we can see that since if we said earlier that our vector function is probably going to look like the cross product of two other vector functions, a and b, based on just how the equation that we're trying to solve looks. And so based on that, then we can get the product rule from Griffiths. It's product rule 4 for the divergence of a vector function that can be expressed as the cross product of two vector functions. And so that's b dotted with the curl of a, subtracting a dotted with the curl of b. Okay, simple enough, and now we're just going to do the procedure we've done a couple times already and put these two ideas together. And so we would get volume integral, this part would become b dotted with curl of a minus, I'll put a detail there, separate these terms, another volume term, detail equals closed loop integral over the surface that bounds, creates the boundary of that volume, of a cross b, ooh, no, that's wrong, dotted with the dA vector. All right, so that is looking good. And then just to get it into the form that the problem statement has, we will just add this term to the other side, and I won't take the time to write this out because it's it's a lot of writing, and it's pretty obvious how you would get from this line to equation 161, which is the one that it wants you to solve for. And yeah, that looks right to me. And so yeah, and so I think this is a good question. It does a good job of sort of showing you these concepts that might be, look threatening and even confusing at first. I think the problem does a good job of taking you through step by step how these equations are derived and how they're simply natural extensions of concepts that you would have already learned in introductory calculus. And so for that reason, I think it's a good question. Not necessarily a hard question, but conceptually just a good question to affirm and reinforce the underlying concepts that go into deriving these equations. I think that'll be all. So, thank you for watching.